Hi everybody, in this next set of videos, we're going to look at trigonometric equations. Now, trigonometric equations are just equations that have trig functions that we're trying to solve. And the idea of a solution is the same thing. Your solution is the value that would make that equation true. Now, the reason that trig equations can get so tricky though is because trig functions are periodic, meaning that they continue on forever. So actually most trig equations, although I shouldn't say all, but in case there's exceptions here or there, but in general, for our simple trig equations like this, they tend to have infinitely many solutions. So what I have here, just a quick graph. In blue, I graph the left side of the equation. So you see y equals sine x. And then in red, I graph the right side of the equation, which would be y equals 1/2. And every place that these two sides meet and are equal is where you have a solution. And you can see that those two lines, or one line and one curve, are intersecting many, many times. So it's not to scale, so bear with me. But my first intersection occurs here when x equals pi over 6. And then it occurs again when x equals 5 pi over 6. It occurs again when x equals 13 pi over 6. And then next at 17 pi over 6, etc. And again, this is going to keep going and going and going. So this is why it gets really complicated, is because often you don't necessarily just have maybe one answer. It really depends on the equation. You could have infinitely many answers. And you'll notice that sometimes we'll be solving for equations and they'll just say solve, and there's no restriction on the domain, so that they want all possible answers. Other times they may restrict the domain and just say, oh, x values are only between 0 and 2 pi, or negative pi to pi, or something like that. So you do want to be careful to see for what values you are solving for. Now, let's say you have an example like this, and we don't want to restrict the domain. So we're not looking at just a small little part of the graph. We want to look at the entire graph. So you have infinitely many solutions here. How do you express something like that? Well, what you do first is you think about the original period of the function. So our period for sine is 2 pi. And if you think back to our sine graph, so quite a few videos ago now, you think about the graph of the sine and cosine functions, we did make a table a while ago about common sine values. And what we did is we did that table from 0 to 2 pi. That tends to be the most common place when you're looking at your sine function, is from 0 to 2 pi. So I would start with that first. Just start with that one period. That's really what you need to start, and find all the solutions on that one period. Now, for 0 to 2 pi, you have two initial solutions. So you have your first solution, pi over 6, and then you also have your second solution, 5 pi over 6. After that, if you notice your next solution, so 13 divided by 6 is bigger than 2. So is 17 divided by 6 bigger than 2? So you're over 2 pi for these. They're outside that initial period. And same thing if you're below, right? You would be in the negatives there. This one would be negative. So what you do is you find your solutions in an initial period. And usually we use the one that's most common. So for sine, that's 0 to 2 pi. You find that first. And then what you do is you add to it the period. So this is going to repeat every 2 pi. So it's going to also be the same result 2 pi later. And again, 2 pi after that. But I can keep adding 2 pi or subtracting 2 pi over and over and over again. So what we do is we often multiply it by n. And then we let n run through all possible values. N is 0, n is 1, n is 2, n is -1, +2, etc. So you'll get all those other values there. But this is based on that period, right? Now, most of our trig functions have period 2 pi, but some of them do have period pi, so that's why you have to be a little bit careful there. So this is the trick for the trig functions. It's not so much the solving, although again, it is a little bit more complicated because it's trigonometry, but it's remembering all of our solutions. And graphs can be really helpful. So I do recommend doing this, using Desmos or another graphing tool. If you're kind of getting stuck and you're like, oh, I'm not sure what to do here, graph the left and the right side. Where those two sides intersect, those are all your solution points, and that can kind of help you get started and think about, okay, well, what would be the set for one period? And then if you need to expand beyond that, you can expand beyond that like we did here. One thing I will note as well is if you write it as 2 pi n or 2n pi, it's the same thing. So sometimes books will write it different ways, but they are the same thing. It doesn't matter how you write that piece. So let's actually get in and solve a full example here. All right, so here's our first equation. And what we want to do is think of it like a regular equation. So typically we like to isolate the x stuff together and get numbers to the other side here, right? If you had parentheses, you would still multiply through and use your regular steps. So here I have 2 sine x's. I would really like to get those together. So I'm going to go ahead and bring this to the other side. So I'm going to subtract 5 sine x from both sides. Now 3 minus 5 is -2. And then I'll bring everything else down. So -2 equals minus or -1. Notice that I didn't actually change the sign x. I just worked with the numbers out front. And now I'm going to go ahead and I want to bring my numbers to the other side. So I'm going to add 2. And I have -2 sine x equals 1. And then finally, now here, you're not really solving for x, you're solving for sine x instead. It's really hard to kind of get rid of the sine piece. We'd have to use inverses. So what we're going to do is we're going to divide both sides by -2 and really just focusing on trying to isolate the trig part instead. Now you could use an inverse function here, right? If I took inverse sine of both sides, that would help me solve. But the problem is when you do that with your calculator is it usually gives you the decimal answer. And a lot of times we like the exact answer. So the better way to do it is to kind of think back in your mind and say, okay, well, what angles give me -1/2? And again, you have, I hope, tables like this already written down from previous videos. I'm going to show you mine. This is from the videos on graphs of sine and cosine functions. And what we did here for sine is we did make a table of common values on that first period from 0 to 2 pi. So this is going to be really helpful for you. And remember, I really want to know where is the value of -1/2. So if I look at this sheet here, I see that -1/2 is down here at 7 pi over 6, and then again at 11 pi over 6. So those are the 2 times it occurs on that first period of 0 to 2 pi. So I'm going to go ahead and write those down. If you don't have this saved from the previous video, pause here, copy this down, take a picture, do something so that you have easy access to these common values. The other thing you could do too is you can always graph that sine function. Desmos can be really helpful with finding values and clicking along the way. It usually will give you a lot of answers in terms of radians and pi, so that can be helpful too. All right, so we saw that our 2 values for that were 7 pi over 6 and 11 pi over 6. Now, this equation here does not note or restrict the domain, right? It just says solve. Sometimes you'll see a domain restriction, and you'll have to keep that in mind. But here, we don't have that yet. So they want all possible answers. And again, you want to remember for sine, the period is 2 pi. So our final answer will be 7 pi over 6 plus 2 pi n, and also 11 pi over 6 plus 2 pi n, or 2n pi, whatever you want to write. So again, these are our 2 answers on the first period, but that function continues forever. And because the sine function has period 2 pi, that's why we're adding 2 pi n. So you want to be really careful what function you're dealing with. For sine, we typically start between 0 and 2 pi, and then our period is going to be 2 pi. So that's what's getting added on here. Let's do another example, or we'll do a few examples, of course. All right, so here we're looking for when we're solving tangent of 3x equals 1. We do have a domain restriction, so we only need answers between 0 and less than 2 pi. Now, be careful here. You do want to remember that for tangent, though, the period is pi, not 2 pi for tangent. So think back to, was a lot of information in our brains at this point, but we know tangent has period pi instead. So we are going to run through more than one period here. And another thing to watch out for that's different is, notice here it's not just tangent x. That's more straightforward. It's tangent 3x. Whereas in our last examples, we talked about just having sine x, here sine x, right? There was no other number with the x. So that's an important change to note here. I can't divide by 3 on both sides. That doesn't work. When that 3 is inside the tangent function with the x or with any function, you can't just divide it out, only numbers that are on the outside. So this is as simplified as it can get. So what you need to do here is you need to think about your tangent values. And again, if you have a little chart, you can go ahead and take that out. So I was just looking through my notes as I paused the video, and I did find one of our charts for tangent. And again, we've made a few of these, but this is one from our video on graphs of other trig functions. And again, if you look at your tangent function, again, it is periodic. It does have period pi instead. Typically for tangent, we tend to run, between negative pi over 2 and positive pi over 2 here. So what you can see here from my list is I just did from 0 to pi over 2. And what you see here is we're looking at that value 1, and tangent x is equal to 1 at pi over 4. So that is about like, let's see, maybe like right here. Okay. Now, if I look, that would be the only value in this first initial period where it is actually equal to 1, right? Here it goes down, so you're all negative there, and then you go up. And of course, you're going to repeat, so we're not done here. We do need to get the other values too. But in our main initial period for tangent, we tend to look at negative pi over 2 to pi over 2. And you see that there is only one value of 1, and it's right here at pi over 4. So I'm going to go ahead and use that information. Okay. So I know here that tangent of theta equals 1 when theta is equal to pi over 4, right? So here, my theta, though, is 3x. It's not just x, or else I'd be almost done. It's a little bit more complicated. So I know that what's happening is that, well, 3x, that's my theta. That's our theta here, is equal to pi over 4 in this case. That must be the solution. I do have to solve it, though, right, and do a little bit of work here. The other thing I want to remember, though, is that we are also periodic with period pi. So I'm adding in pi times n, or n times pi, whatever you want to do. So remember, our period here is pi or tangent instead of 2 pi. So we're going to add in that piece. And I do add it in before I solve for x. So now that I have that added in, I'm going to divide everything by 3. So make it a little easier. I'm just going to multiply both sides by 1/3. I'm going to distribute here. So 1/3 times pi over 4 will be pi over 12. 4 times 3 is 12. And then here, I'm going to just move the n out front. It's going to be n over 3. 1 times n is just n, and then pi as well. Or you can put the whole thing over the denominator. Again, there's a few different ways that you can write it. So this is our final answer. If I was finding all values, then this would be it. I'd be done. I do have a domain restriction here, though, and I only want to list the answers from 0 up until 2 pi. So how can I do that here? What you're going to do is you're going to let your n run through different values. We typically start with n is 0 because, again, I'm looking for just the positives here. I don't need any negative values. So n is 0 is that initial one that we always start with. So you would have that your x value is pi over 12 plus 0 times pi over 3. Of course, this all cancels out. So it's just pi over 12. Your n equals 0 will always give you the first value that we already found. And then you try n equals 1. So we have pi over 12 plus 1 times pi over 3. You do need to do a little bit of common denominator work here. So that's going to be 4 pi over 12. So you have 5 pi over 12 as your next answer. This is fine because this is still less than 2 pi, right? That was my restriction. So I'm going to keep going. Then I plug in n equals 2. Again, I need common denominators. I'm going to multiply by 4 here. That's going to give me 8 pi over 12. So I'm at 9 pi over 12. And I can go ahead and simplify that by 3. So I have 3 pi over 4. And I'm going to continue this process. This is still less than 2 pi. So I'm going to keep going. I'll let you do some of the arithmetic on your own. When I do n equals 3, let's see, I'm going to get x is equal to, again, pi over 12 plus 3 pi over 3, which is just pi. And when you add those together, you end up with 13 pi over 12, which is still less than 2 pi. When I do n equals 4, I have pi over 12 plus 4 pi over 3. And when I do the math there, I end up with 17 pi over 12, which is still less than 2 pi. And when I do 5, I end up, let's see, with 21 pi over 12. I can't simplify that one by 3, so I end up with 7 pi over 4. And again, that's still less than 2 pi, right? Because 7 divided by 4 is less than 2. Now, when you try to do n equals 6, what happens is you're adding a 2 pi here, right? So you're doing pi over 12 plus 2 pi. You end up getting 25 pi over 12. And this is now too big, right? Because it is greater than 2 pi. It's outside the range that we're looking for, or the domain that we're looking for. So we can stop at this point. And again, I don't need to do negative ends because my specific domain was starting at 0 to positive 2 pi. And when I looked at my values for tangent, I got the smallest one within that range already. So I don't need to go negative here. So for this one, again, this one was a lot of work because not only did we have to figure out the angle a little bit in more detail, but because they didn't want all the answers, they only wanted answers between 0 and 2 pi, we have to specifically find those. So it was pi over 12, 5 pi over 12, 3 pi over 4, 13 pi over 12, 17 pi over 12, and 7 pi over 12. Those would be the specific answers here. All right, let's do a couple more. Again, these are pretty tricky. So I'm just going to do a bunch of practice really in these videos for you today. Okay, so here we have something similar. I didn't mention this in the last one, but notice that, sine is by itself here. Last one, tangent was by itself. There really wasn't anything to do, right? There's no like terms to combine or anything like that. I can't get rid of this 2 because it's inside the sine function. If it was outside, yeah, I could get rid of it. But because it's being plugged in with the x, I can't get rid of it. So you have to kind of think and say, okay, I need to figure out, well, sine of theta is equal to root 3 over 2 when theta is what? When the angle is what? And again, you can go back to one of your charts. For sine, the basic sine function, the first period is between 0 and 2 pi. So if I look here, again, I'm going back to my previous notes, looking for root 3 over 2, I see that occurs at pi over 3, and again at 2 pi over 3. And that's the only time that it occurs within 0 to 2 pi. Now, the nice thing here is with the tangent one we just did was a little bit harder because your period was only pi, but you were running through 2 pi, so you were going through a couple period cycles there. Here, we're just going through the first period of sine. So I actually have the 2 angles that I need. But the problem is that my answer wasn't just sine x, it was sine x over 2. So I have a little bit more work to do then. So my answer here is pi over 3 and 2 pi over 3. But like with the last one, it's not just straightforward. I have a bit more work to do because it's sine of x over 2. So I have to go ahead and set that up. So I have 2 equations. Oops. And remember that we're periodic over a periodic of 2 pi here with sine. So again, we're going to add that 2 pi n. Now I do want to get x by itself. So here, because it's a fraction, I'm actually going to multiply both sides by 2. And I'm left with the fact that x is equal to 2 pi over 3. And then to multiply that 2 through, so plus 4 pi n. And then also, x is equal to 4 pi over 3 plus 4 pi n. Now, your initial answers should be there because we started with 0 to 2 pi already. We looked at that first group. So when n is equal to 0, your first answer is 2 pi over 3. And your second answer is just 4 pi over 3, right? Because this piece cancels out. Now, what happens is when you go to n equals 1 here, it's actually too big because you're getting 2 pi over 3 plus 4 pi times 1. And then also 4 pi over 3 plus 4 pi times 1. So think about this. If we want our range, or our domain, excuse me, to be between 0 and 2 pi, well, adding 4 pi to this is going to be way too big already, right? Our initial values were fine. We know they're within the range, but if we add 4 pi, we're way outside this initial domain that we're looking at. So our only 2 answers here are 2 pi over 3 and 4 pi over. And again, that's for this interval. If we were unrestricted, right, if this wasn't here, then we would leave our final answers like this and this. That would be done. But because we're restricted, they want you to list up the specific examples for within that whole group. Again, so just be careful of how it's worded. You can see in the last 2 examples we did, we had that restriction on the domain. So they want you to list the exact values for everything in that domain, in that group. Whereas with our first set of examples, right, we didn't have that restriction. There was no restriction. So they want you to list everything. So you would leave it with the 2 pi n or the pi n, whatever you're doing. So be careful of those distinctions there. They do make a really big difference as you go through.